Okay, so let's just check out. Yeah, we had discussed about the angular variables to describe circular motion, including angular position, angular displacement, angular velocity, and angular acceleration. So let's pick it up with a recap of these concepts. Then we'll move forward. So we had seen that circular motion is defined as a motion in a two-dimensional plane such that the distance from a particular fixed point remains constant. So that particular fixed point is called the center of the circle, and the path described by such a motion becomes what is called a circular path, where if at any instant a particle is present at this particular point, then its coordinates are such that the position vector with respect to the center has a fixed magnitude. So the particle is describing a circular path like this, then at any instant of time, the position with respect to the center of the circular motion is such that magnitude of r is constant. So that becomes the equation of the circle. Or we can say the circular path with the origin as center. And the radius is r. Now we come to the angular parameters. So the angle made by the position vector with respect to the x-axis is called the, yes, so I will send the recording and the notes of the previous lecture in just some time. Okay. So the angular parameters, we start by describing angular position, as we said. Then we have angular displacement. That is the change in angular position. So that is like that. Okay. Then we have angular velocity, which we denote with a single symbol omega, which is instantaneous rate of change of angular position with respect to time. And we have angular acceleration. So these two are defined in radians or expressed in radians. This is in radians per second, and this is in radians per second square. Okay, so this is a quick recap of the introduction to circular motion we had seen last time. Just begin by understanding these, then we'll look at a couple of application problems based on this. Okay, so let's understand these concepts with a couple of questions. So before that, a couple of further things to note down. So this can also be written as second derivative of position with respect to time. And also by using chain rule, alpha can also be written in terms of d omega by d theta. Okay. So just as in 1D motion, we had position, we had displacement equal to change in position. We had instantaneous velocity as instantaneous rate of change of position or displacement with time. And we had acceleration as dv by dt. So acceleration could also be defined as second derivative of position, or by using chain rule, also be defined this way. So these equations are, you can say in a sense, they are comparable. Okay. But with respect to angular parameters, whereas in 1D motion, we had the 1D parameters. Whereas in circular motion, we have the angular parameters. So now naturally, if angular velocity is uniform, okay, the motion is called a uniform circular motion. And angular velocity being uniform also means that angular acceleration is zero. So in uniform circular motion, angular acceleration is zero. And angular displacement becomes the uniform angular velocity into time. So for example, you have the motion of the seconds hand of a mechanical clock. So you have covers 2 pi radians of one full circle every 60 seconds. Angular acceleration is zero. So for example, in a time interval of 15 seconds, the angular displacement equals to pi by 2 radians or 90 degrees. Okay. As you all know, a seconds hand of a clock in 15 seconds covers an angular displacement of 1/4 of the circle or 90 degrees, pi by 2 radians. These are examples of uniform circular motion. Okay, next situation we'll see is circular motion with uniform angular acceleration. So alpha is constant or uniform, and at t equal to 0, let's say the angular velocity is omega naught. So therefore, is being constant, we integrate this at t equal to 0, angular velocity is omega naught. At t equal to t, angular velocity is omega. Okay, the alpha outside the integration because it's uniform. You can see we'll get this kind of equation, which is the circular motion equivalent of v equal to u plus at. It's the angular equivalent of the equation v is equal to u plus at. See, we'll get equivalents of these equations now.
So these are just kinematical equations, right?
Yes, these are kinematical equations for specific situation. In this case, when alpha is constant. Because we can only use this when we have a circular motion with uniform alpha. Now, secondly, omega, which is rate of change of angular displacement, sort of a function of time. So integrating this equation now will give us the displacement, that is angular displacement as a function of time. So we can see that after a time t, the angular displacement delta theta is omega naught t plus half alpha t square. On integrating this and putting the limits. So this is the second equation, which is corresponding to the second equation for uniformly accelerated 1D motion, which was S is equal to ut plus half at square. Okay, and the third equation we can correspondingly get like this, that So you can just remember these three equations as the angular version of the standard three equations that you've seen in uniformly accelerated 1D motion earlier in kinematics. Only now, instead of the motion happening along a straight line and a 1D parameters, it is now happening along a circle, and the parameters are the angular parameters. Okay, so let's look at a quick example. A particle starts from rest at time t equal to 0, moving at a uniform angular acceleration pi by 4 radians per second square, okay, along a circle of radius 10 meters. Find its angular velocity omega at t equal to 1 second. Find its angular displacement from 0 to 2 seconds, and find the distance traveled from 0 to 2 seconds. Yes, Akshat, very good. That's correct. So you can see here the data we will substitute that because it is starting from rest at t equal to 0. So we'll take omega naught equal to 0 at time t equal to 0. Okay, and it has a uniform angular acceleration. This thing is uniform, that's important. So we'll take and this is uniform. So once it's uniform, we can make use of these relations. Okay. Make use of these. So at t equal to, for example, 1 second, the angular velocity will become pi by 4 radians per second. Now distance traveled at t equal to 2 seconds. You have to understand this. You have to interpret this. Okay, that what is happening is that, say, if it's starting from here at t equal to 0, then it's covering an angular displacement pi by 2 or 90 degrees. T equal to 2 seconds. So the distance traveled is this now, the arc length. This distance traveled, it will be basically 1/4 of a circumference.
Sir,
Yes.
so in the last question, the distance traveled would be theta by 360 into pi r square for the theta in degrees.
If the pi r square is area, circumference is 2 pi r, no?
2 pi. Oh.
1/4 of that. Huh?
Yes, sir. Yes.
I think that's the calculation mistake you made. Otherwise, your answer would have been correct. Okay, so this is an example of uniform circular motion. Of uniformly accelerated or uniform alpha in a circular motion. Okay. So now that we are done with the angular parameters, we will move on to the next few things in circular motion. So first, we will learn something called about the radial and tangential unit vectors. These are two very important terms, both in describing the motion itself as well as when we are going to apply Newton's laws and talk about the net force and acceleration and all those things in circular motion. So let's understand what is radial and tangential unit vectors. So if at a certain point of time, a particle in circular motion is located at a certain angular position theta, so therefore its position is here with respect to the center of circular motion in the plane of the circle. So this is the position vector r. Then we define two important unit vectors here. Unit vectors are vector of magnitude 1. We define the radial unit vector, which is the vector pointing along the radial line. And we define the tangential unit vector, which is the unit vector or vector of magnitude 1 pointing along the tangent to the circle at that particular point. So as you can see, they are mutually perpendicular. So this is called the radial unit vector r cap, and this is called the tangential unit vector theta cap. So radial unit vector r cap, it is a unit vector along the radial line or axis. So this is your radial line over here. And the tangential unit vector is a unit vector along the tangent to the circle at that given point. So this is the tangent to the circle, as you can see, this line here. So now these two are given by a special formula. Okay, and that formula is very simple to understand because it's a vector of magnitude 1. So if you look at r cap and theta cap separately with respect to your xy plane, you'll understand r cap is a vector of magnitude 1 at an angle theta, whereas theta cap is a vector of magnitude 1 which is perpendicular to it. So this angle is 90 degrees and its magnitude is also 1. So r cap is given by the formula cos theta I cap plus sin theta j cap, which you'll get when you resolve it, and theta cap is given by the formula minus sin theta I cap plus cos theta j cap. So you can see that this one is actually cos of 90 degrees plus theta. This one is sine of 90 degrees plus theta. So that's how we get these. Okay, so these two unit vectors are important because they give us the two important directions at any point in a circular path. One is the radial direction and one is the tangential direction. So if we want to define any vector according to these directions, we use these unit vectors. Not exactly. It doesn't come out to be the derivative because theta itself is a variable quantity. So we have to use chain rule. Okay, but yeah, we have the relation that theta cap is in fact, I mean, dr cap by dt. The derivative of r cap is omega into theta cap. Actually, we will discuss about that also. In fact, that is coming up next. So once we have defined the unit vectors like this, next thing we'll do is the application of these unit vectors, why it's important. Because when we are describing things like position, velocity, acceleration, etc., this becomes important. Okay. So position vector, velocity vector, instantaneous velocity, that is v, and acceleration vector. Not the angular position, not the angular velocity, but the velocity itself, the acceleration itself in a circular motion. So understand these things. So position vector is something very easy to understand, but we'll also look at it in context of the angular parameters as well as the unit vectors, the two unit vectors we've discussed about this now. So this is a circle of radius capital R, let's say, then magnitude of the position vector at any time is R. So if the angular position is theta at some time t, this is where the particle is located at time t, then the position vector at that time is r cos theta I cap plus r sin theta j cap, or the position vector is simply the radius multiplied by the radial unit vector. So now we come to velocity. Instantaneous velocity is defined as rate of change of position. So that we have to now differentiate this whole term, r cos theta I cap plus r sin theta j cap. So this is where our chain rule application now comes in when we differentiate. So see, when we apply the derivative inside the bracket, capital R is a constant, so it just applies directly to cos theta. And then again, capital R is a constant, j cap is a constant, so it applies here. Okay. Now, when we are differentiating this, we will make use of chain rule. Differentiation of cos theta with respect to time will become derivative of cos theta into d theta by dt. So that is minus sin theta into omega. And likewise, differentiation with respect to time of sin theta, that will become derivative of sin theta into d theta by dt. It will become omega cos theta. So these two values now have to be plugged in. This and this are the values for this term and this term. So we plug them in here. This equation becomes further we can see that if we take r omega common, left with this. Now, if you compare this with the above, you can see that what we have in the bracket there is the tangential unit vector, theta cap. This is sin theta and cos theta, my mistake. This. So this is an important derivation in circular motion. It shows us that the velocity's direction is tangential and its magnitude is equal to r omega. note of this, please, people, to this point. Okay, so now let's understand this in more detail. So when we look at the direction of the velocity vector, because it's along theta cap, or is the tangential unit vector, you can understand that the velocity vector is always perpendicular to the position vector at any point of time. It's always perpendicular to the r vector because it's lying along the tangential direction. Any point of the circular motion, the direction of the velocity will be along the tangent to the circle. So this tells us this important aspect over here, that the direction of the velocity vector is always tangential. That is, it is along the tangential unit vector theta cap at any instant during the circular motion. And additionally, the speed v, which is the magnitude of velocity, is r omega. So there's a relationship between the angular velocity and the magnitude of linear velocity, and that is this equation, which is also very important in circular motion. So just make an additional note of these 2 points before we move on to acceleration. Okay, so this is about the velocity and acceleration. I mean, about the velocity. Now, before we move on to acceleration, we will understand a couple of more things. In a uniform circular motion, by definition, omega is uniform or constant, and that implies that alpha is zero. Now, omega is uniform also implies that speed is uniform because v is equal to r omega. So in a uniform circular motion, what happens is that the speed is uniform. But again, keep in mind that velocity is not uniform because its direction is always turning. Okay, so it's wrong to say velocity is uniform in uniform circular motion. Speed is uniform or magnitude of velocity is uniform. And therefore, the motion is periodic in nature. It means it repeats in cycles. It's periodic with a time period of circumference upon speed, which is the same thing as 2 pi by omega. So this is an additional property of uniform circular motion that you need to understand. So obviously, as opposed to this, in a non-uniform circular motion, angular speed is variable because alpha is not equal to zero. So speed is also variable. It has variable speed and no definite time period. So the motion is not periodic. Okay, so now we come to the main important part about this kinematics part, which is acceleration in circular motion. So this acceleration part will actually classify in two categories. We will first look at acceleration in uniform circular motion, UCM. So the general definition of acceleration we'll use, but we'll apply it for the specific condition of uniform circular motion. Now remember, uniform circular motion had the condition that omega was constant, v, the speed was constant, alpha was 0. Okay, so we'll apply these conditions here. So acceleration, which is rate of change of velocity with respect to time, becomes so here we understand that v is r omega theta cap, where theta cap was minus sine theta I cap plus cos theta j cap, and d theta by dt is omega. So just applying that same definition here. So this time when we look at the acceleration, what we can do is we can take r omega common outside because omega is uniform. So it's differentiation of sine theta. This term directly gets multiplied with I cap, and then with a minus sign, and then differentiation of cos theta with respect to time. This term directly gets multiplied with j cap. So the acceleration becomes r omega. Now differentiation of sine theta is cos theta, but applying the chain rule, there'll be an extra d theta by d theta, and differentiation of cos theta is minus sine theta. So again into a d theta by dt term, this gets multiplied with j cap. So this term becomes like this. And d theta by dt is omega. So further this gets simplified to so this tells us the important thing here, that minus r cap. So that is radially inwards. So that is why this is called the centripetal direction, because it points towards the center. Which is why this acceleration is a centripetal acceleration, because it points towards the center. Just to understand this visually also. This is our position vector at any point of time. We're dealing with a uniform circular motion. Then our acceleration vector is pointing towards the center. It's radially inwards. Whereas our velocity vector, as we've seen earlier, is tangential. Okay, so these are the important relationships between these quantities. Okay, so that is about centripetal acceleration in uniform circular motion. So just as a simple example, if we look at something like this, that a car moves on a circular track, say of radius 25 meters at a uniform speed of 36 kilometers per hour. Find its angular speed, its acceleration. That is the magnitude of the acceleration, how much that is. Just try out this question, people. Okay, so this should be a fairly simple question. So you can see here that the speed, which is 36 kilometers per hour, when you convert it, it's 10 meters per second. So the angular speed will be 10 by 25 or 0.4 radians per second. And angular and linear acceleration is p square by r or omega square r, whichever. So we have an acceleration of magnitude 4 meters per second square. So basically, as this particular situation unfolds, car is in a circular track of radius 25 meters, going at a uniform speed of 10 meters per second. So uniform circular motion. And at any point of time, it has an acceleration vector. It's pointing towards the center. So magnitude of this much. Okay, so fairly simple direct application, as you can see. Next, we will move on to acceleration vector in a non-uniform circular motion. Okay, people. So now let's come to the next part, acceleration in a non-uniform circular motion. So let's keep track of non-uniform circular motion being a case where omega is variable. So alpha is not equal to 0. So v is also variable. The linear speed is also variable. And in fact, we have d omega by dt is equal to alpha. Okay, so again, acceleration being rate of change of velocity, it is rate of change of r omega into this unit vector minus sine theta I cap plus cos theta j cap. So this time when we apply the differentiation, what we'll have to do is we'll have to use the product rule because omega is also variable. Omega is also variable. And theta cap, which is minus sine theta I cap plus cos theta j cap, this is also a variable quantity. So it will become like take the capital R outside into differentiation of first term into second term. Plus first term into differentiation of second term. So this becomes R into alpha. Whereas this is really the same term that we've seen before. When we differentiate this, it becomes minus omega cos theta I cap minus omega sin theta j cap. So this becomes like R alpha so the minus sign here. So now you can see that the acceleration has two components. Okay. This is what we call the tangential component, and this is what we call the centripetal component. Okay, so in non-uniform circular motion, the net acceleration is the sum of two components, tangential and centripetal. The net acceleration vector has the two components, tangential and centripetal. Okay, so the final aspects to remember about this. The magnitude of the centripetal acceleration, which is omega square r, can also be written as v square by r or v into omega. And the magnitude of the tangential acceleration, which is r alpha, can also be written as this, because alpha is d omega by dt. Capital R is constant. So tangential acceleration equals to rate of change of speed. The magnitude of the tangential acceleration is equal to the rate of change of speed, whereas the magnitude of the centripetal acceleration is v square by r. So in general, what we understand here is that centripetal acceleration plays the role of turning the direction of the velocity vector continuously. Whereas the tangential acceleration plays the role of changing the magnitude of speed in a non-uniform circular motion. This is another important thing to remember about the role played by two of the individual components of acceleration. And finally, the magnitude of the acceleration, the net acceleration magnitude. Okay, so this completes the kinematics part of circular motion. And with the application of these things from the next lecture onwards, we'll start looking at dynamics. That is, we'll start looking at the application of Newton's second law, that net force is equal to mass into acceleration. Okay. So that's it for today's session, people. Wish you all the best. Please make a note of these things carefully. I will send you the notes and recording of this also soon. You can start with the questions from circular motion chapter of H.C. Verma. You can do questions 1 to 22 now based on this from the H.C. Verma exercise of circular motion chapter. That's it for today's session, people. Wish you all the best.
Thank you, sir. Sir.